Hello everyone. My name is Vivek. I'm a part of the Snorkel research team. Specifically, I work on computer vision related problems as an applied research scientist. But we're leading this, doing this AI guest speaker series to, allow leading researchers in the field to come and talk to us at Snorkel about what they're working on, what kind of ideas they have, and also to see if there's any overlap from our side in the research areas that they're talking about. So today we're super excited to have Nihal talk to us. Nihal is currently a Ph.D. student at Brown University, being advised by Professor Stephen Bach, who is an affiliated researcher with us at Snorkel. So today Nihal will be talking about Bonito, which is an open source model for converting unannotated text into task-specific training datasets for instruction tuning. And the goal here is basically to enable zero-shot task adaptation of LLMs on the user's specialized and private data. Obviously, this is very similar to what we do at Snorkel as well, and has a lot of overlap with some of our goals as well. So yeah, without any further ado, Nihal, the stage is yours. Go for it.
Thank you for the introduction. Today, I'm going to be talking about our work learning to generate instruction tuning datasets for zero-shot task adaptation. This work was done at Brown with Yiyang Nan, Avi Trost, and Stephen Bach. In this talk, I will show you how to adapt large language models to your data without human annotations. Here's a brief outline of the work. I will keep coming back to this slide. Now let's understand the motivation for this work. There's a growing need for specialized LLMs. People from all walks of life want to use LLMs in their work. Professionals from areas like legal, finance, healthcare, insurance, and more areas want to use LLMs to assist them in their work. Existing LLMs are trained to be general so that they can serve a wide range of use cases. The data used to train these models is obtained from internet containing data sources such as Wikipedia articles and newspaper articles. This is a one-size-fits-all approach. In contrast, we want our LLMs to do well in domains like medicine and law, where the data is highly specialized and often requires implicit domain knowledge. This one-size-fits-all approach does not perform well in every specialized domain. Recently, several papers have shown that these generic LLMs still lag behind in performance when compared to specialized language models. And even if the biggest companies like Google, Anthropic, and OpenAI came out with their fancy API-based models and improved the performance in specialized domains, we might not benefit from it. This is because people cannot share their data with other organizations, as it might break privacy regulations and breach contracts. Some examples of such data include electronic health records, legal documents, and private research data. We can train specialized LLMs from scratch by using self-supervised learning objectives like next word prediction from data, which is obtained from specialized domains. And there are several successful specialized models like Bloomberg GPT for finance, PubMed GPT for biomedical language models. And this works reasonably well when trained on lots of data. But this approach is both time-consuming and resource inefficient. For example, Bloomberg GPT trains on 512 A100 GPUs for 53 days, and we don't want to do that. Instead, you could start from a pre-trained language model and continue adapting it with self-supervision. This again shares the same drawbacks as training the model from scratch. Instead, you can do instruction tuning or supervised learning with instructions. This is what many off-the-shelf models do. Now, I'll briefly explain what instruction tuning is, and then show how people have adapted it to specialized domains. In this approach, we train the model with multiple instruction response pairs. These instructions could be something like, how would you rephrase that in a few words? Or on a scale of from 1 to 5, how would you rate this review? So once you train the model on enough number of instructions, this training enables the model to generalize to new tasks. So at test time, you can ask new tasks that the model has never seen before. Typically, these instructions come from the general domain. Some people have taken this idea further and trained models with data from specialized domains. There are several successful applications of this approach. MedPalm from the medical domain, K2 from the geosciences space, and Climate GPT from the climate domain. However, collecting instructions in specialized domains is very expensive. This is because instructions in specialized domains have to be annotated by subject matter experts. Here's a quote that I find very interesting and insightful from Climate GPT. Climate GPT authors actually tried to use non-experts to create instructions from academic research papers and technical reports. But they quickly found out that these annotators who are not experts struggled with these documents and ended up changing the data itself, meaning they changed the data to something more simpler that the annotators could annotate. So we have two possible choices, self-supervision and supervised learning. Both have their pros and cons. While self-supervision has low data cost, meaning we don't have to annotate data, it is computationally expensive and provides no explicit instructions. On the other hand, supervised learning approaches like instruction tuning can create high-quality models, but collecting training data is incredibly expensive in specialized domains. This begs the question, is there a middle ground here? Can we get the best of these two approaches? Can we achieve low data cost while still developing a high quality model? And that's exactly what we do here. We create Bonito, an open source model that converts users' unannotated text from specialized domains into synthetic instruction tuning datasets. Now I'll show you how simple the workflow is. First, we have the train Bonito. I'll explain how the training works for this model. Then we have the unannotated text from the target domain. We also have a target task type or a target task attribute. Here we have natural language inference. And then when you pass these the unannotated text and the target attribute to the Bonito model, it will generate an instruction response pairs. After generating sufficient number of instruction response pairs, we get a synthetic data set from the specialized domain. And then this can be trained, we can use this to train another model to create the specialized LLM. It's so simple. Now at this point, you might be wondering, how does Bonito learn to generate tasks? Our key idea is to create meta templates that will generate the data sets which will be used to train Bonito. Let's consider the data set from Hugging Face. Here we have Hugging columns such as question, answer, and passage. Instruction tuning datasets are constructed by using Jinja templates. These Jinja templates convert datasets into instruction response pairs. Prior to this work, we created a repository called prompt source or P3, where we annotated multiple Jinja templates for several datasets on Hugging Face and elsewhere. Now in this Jinja template, we have the input and the output along with the corresponding columns from the dataset. In this work, we identify all the Jinja templates in P3 that have a passage or reason over a passage. Now that we've done that, here's what's cool. We remix the template to create a meta template. In the meta template, we have the passage and the task in the input and the generated instruction response pair in the output. We also have a placeholder for the context, which is just to indicate where the context goes. And we repeated this process for a total of 323 templates and 38 datasets. Once we have the meta template, we simply replace the columns in the template to create training examples. With this approach, we were able to generate 1.6 million examples. We call this dataset the conditional task generation with attributes dataset. The dataset has a total of 16 task types commonly used in natural language processing. And we train Mistral 7B model, an open source model on this dataset to create Bonito. Now let's look at a few example generations from Bonito. Here's an abstract from PubMed. You don't have to read it. And also, if you're not familiar with PubMed, it's a database containing biomedical and life sciences papers. what I want you to do is pay attention to the complexity of this paragraph. As you can see, it's incredibly complicated. Now we will take this paragraph along with a target task type and pass it to the Bonito model. Here, the target task type is yes, no question answering, and let's see what Bonito generates. As you can see, Bonito generates an instruction response pair. Let's analyze this generation a little bit more. The highlighted portion is the instruction along with the question. This says, having read that, I wonder is LPPLA2 mass and activity levels associated with acute brain ischemia? Now, this is something a subject matter expert might be interested in. Now, let's try to answer this question. First, the sentence highlighted in green is the purpose of the study, and that's exactly what Bonito generated. We study the relationship between LPPLA2 mass and activity levels and the diagnosis of acute brain ischemia in acute phase among patients evaluated in emergency department following transient focal neurological symptoms. This is a really complicated sentence, but this does not answer our question. The answer is actually in the final sentence. The results of our study do not support the early measurement of LPPLA2 mass or activity levels for confirming an ischemic etiology in patients experiencing minor or transient focal neurological events. Now, there is no mention of acute brain ischemia, but what's cool is that Bonito combined elements from the two key parts of the paragraph highlighted in green and generated a challenging question. And also it generated the accurate answer. All we had to do to get this generation was provide the paragraph and the task type. It's that simple. Now let's look at another example, but with a different task type, natural language inference. Here's the instruction response pair. This is a possible hypothesis generated by Bonito about this paragraph. This reads as follows. Based on that information, is the claim elevated LPPLA2 levels are associated with coronary arteries and cerebrovascular diseases. However, they cause a condition of poor health, true, false, or inconclusive. Now, this might not be the most grammatical sentence, but this is still very interesting. It looks like the first sentence contains the answer we're looking for. Elevated LPPLA2 levels are associated with both coronary artery and cerebrovascular diseases. But the hypothesis says more than just this sentence. It also says that this causes a condition of poor health. Is there a causal relationship? Does association of elevated LPPLA2 levels lead to poor health? After reading the paragraph, we find that there is no evidence for or against this claim. Therefore, the answer is inconclusive, and our model generates the correct answer. Now, this is pretty cool because we generated this hypothesis about the study by only changing the task type. Now that we've seen a few example generations from Bonito, let's look at some of the experiments that we consider in this work. We're interested in a task called zero-shot task adaptation. In this task, we have access only to unannotated text and from the specialized domain and a target task type. We then adapt a target model with an appropriate learning method without using any human annotated training data. We consider three task types. The first one is yes, no question answering. We've already seen an example of this. We considered two data sets, PubMed QA and Privacy QA. PubMed QA asks a question about a medical abstract, and we need to say if this is yes, no, or even maybe. And then Privacy QA deals with privacy policies from websites. The user asks questions about a paragraph, and our model should predict if the question is relevant or not. The paragraphs from these datasets are used to generate both the question and the answer with the Bonito model. Next, we consider extractive QA. In this task, we experiment with squad shifts, which contains three data splits: New York Times, Amazon reviews, and Reddit. In this task, we are given a question and a passage. We need to extract text from this passage. This is useful to extract key points from important documents, which is commonly found in industry. We use paragraphs from the datasets to generate both the question and the answer with Bonito. And finally, we consider natural language inference. We've already seen this task before. We consider two data types, two data sets, contract NLI and vitamin C. Contract NLI deals with contracts, and vitamin C is a fact verification data set. In this task, we are given a premise or a passage and a hypothesis about this passage. We need to say if this hypothesis is supported in the passage or not. With Bonito, we use the paragraph to generate a hypothesis along with the answer. We considered two baselines or supervision sources. None, which is the zero-shot baseline, and tapped, which is the task adaptive pre-training. This is a self-supervised baseline. In our work, we use the self-supervised learning objective as next word prediction. We adapt the Mistral 7B model to the target tasks by using only the unannotated text. Now I'm going to show you the results for our experiment. We've averaged the results across all the data sets. The columns represent the different methods, and the y-axis is the performance in F1. The pre-trained model achieves a zero-shot performance of 27.6 F1 points. After training with self-supervision, the model performance improves by 4.4 F1 points. Now, training with Bonito-generated instructions improves the model performance by 39.1 points, which is significantly higher than the self-supervised baseline. To achieve such high performance, we only use the synthetic datasets generated by Bonito. No manual annotation was necessary.
Quick question, Nihal.
Yeah.
So once the model has finished training on Bonito, and once it's finished training on Bonito, at that point you're then going to say you're going to do the predictions on the test set, right, of these datasets, like PubMed
Yes.
QA and whatever.
Yes.
Okay, and at that point, how exactly are you doing the predictions? Are you going to write prompts for these PubMed QA, the Amazon datasets? You're writing custom prompts for these datasets and then getting the answers?
That's a great question. So for the datasets that already had prompts in the test set on prompt source, we just use those. And for some of the datasets where we did not find prompts, we just wrote prompts and then evaluated them using either like the traditional metrics like squad, like to find the score, or we used ranked evaluation for the classification tasks.
Okay, so at the end, after the training, to get the test results, there was some amount of prompting required to get the actual answer. And those prompts could have been different than the prompts that Bonito generated, right?
Yeah, absolutely. So,
Okay.
so we do not modify the prompts that were generated by Bonito at all. So, yeah, we evaluated in a very strict setup where we actually wrote the prompts first and then created Bonito model like months later.
Okay.
Yeah.
All right, thank you.
Now let's move on to a more practical setting where we adapt an instruction tune model to the target task. We create an instruction tune model by adapting Mistral 7B on instructions from P3. If you recall, P3 or prompt source contains instructions from the general domain. And now we have an instruction tune model from the general domain. We will adapt this model with self-supervision and Bonito generated tasks. Here are the results. First, we find that instruction tuning improves model performance on average and performs reasonably well, even on specialized datasets. Now, this is where things get interesting. We find that self-supervision reduces performance by 0.8 F1 points on average. Some datasets, it's more than others. This is because self-supervision interferes with instruction tuning and leads to catastrophic forgetting. This overall reduces the model performance. This is an important result because prior work only adapts pre-trained models with self-supervision to specialized domains. In 2024, we typically don't start with a pre-trained model. We start by adapting an instruction-tuned model because it performs so much more better compared to a pre-trained model. We see that Bonito improves performance by an average of 15.1 F1 points. We don't see issues like catastrophic forgetting because the synthetic datasets are formatted as instructions. Finally, we stress test if Bonito is actually learning about the domain. In this experiment, we adapt specialized models trained on single task types from the general domain. For example, we train Mistral 7B on instructions only from yes-no question answering. Then we adapt it with yes-no synthetic instructions from specialized domains generated by Bonito. We also train an additional Bonito model on single task types and adapt the specialized models with instructions from this model. Here are the results. We find that training on single task types is a very strong baseline. Our results show that Bonito on its own can improve performance of single task type models. Then, if we have a task specialized Bonito, the model performance further improves. This result shows that access to data from specialized domains is in fact helping the model performance. In conclusion, building specialized language models is and is going to be an important problem. Creating synthetic datasets in specialized domains is a good approach as it offers a favorable trade-off between performance and cost. In our work, we showed that synthetic datasets indeed improve the performance of both pre-trained and instruction-tuned models in specialized domains. And you can find our model weights on Hugging Face. We've released the model under Apache 2 license, which is an open source license and allows commercial usage. We've included the training and evaluation datasets on Hugging Face so you can easily reproduce our results. We've also released an easy-to-use package on GitHub. This package is a simple wrapper around the model, and we've released this under an open source license. We've also included tutorials with the quantized model and as well as the actual model. So check it out. With that, I'll conclude my talk. Thank you.
So Chris Glaze asks, it seems like Bonito's success would hinge on a highly performant LLM to synthesize well and answer its own questions accurately. Is that right? If so, do we expect those same LLMs to benefit from its own IFD generated set if it can already answer those questions well?
I think there are two questions. So the first question, could you repeat that? I didn't quite get that.
Yeah, it seems like Bonito's success would hinge on a highly performant LLM to synthesize well and answer its own questions accurately. Is that right?
So that's absolutely true. So we do need a strong base model on which we train Bonito on. So Bonito is two parts. One is we are using a Mistral model, which is incredibly powerful. And we further train Bonito, we train this Mistral model with the Bonito training data set, the conditional task generation with attributes. So yes, you're absolutely right. Like we do need a very strong model to even create like powerful instructions. In the past, we did try to use like smaller models like P5 and it didn't quite work well. So you're absolutely right about that. And what's the second part of the question?
Actually, the second part, I'll just allow Chris to ask. Chris, if you want to ask it, go ahead.
Hey, thanks. Yeah, I'm trying to wrap my head around how this works and like what the net benefit is. So say Mistral is answering its own questions in the synthetic data set, is that right? and so you're creating an IFT data set with answers that Mistral is actually producing. Is that right?
We are creating, you're partially right. We are creating new instruction data sets with Bonito, where Mistral is the base model. We have further trained Mistral with another data set.
Okay, yeah, and maybe that's the piece I'm still trying to like wrap my head around. Is what's the signal that's getting through the IFT data set that's not already in Bonito? Like, how can it, like, if you take the same base model and fine tune it with the synthetic data set that it actually created, how could it actually improve its own performance? If it's if it's already learned, if it can already answer those questions accurately, how can you somehow improve its accuracy on those same questions if the premise is that it's answering its own questions accurately to begin with? So is there something in Bonito itself that's providing additional signal that's not already in the base model's ability to answer questions accurately? You see what I'm saying?
No, I definitely get what you're saying. So the additional knowledge that we are getting is from these unannotated text from specialized domains. So if you are familiar with self-training, in self-training, what you typically do is you have a trained model, and then you get access to additional unlabeled data sets. So having access to this unlabeled data set just improves your model performance just by predicting on pseudo labels and then retraining this model. So we have a similar setup in place.
Yeah, okay, all right, that's the piece I think I was missing. It's kind of the self-supervision component that's actually bringing in the new knowledge that would enable it to answer questions even more accurately than it was before. Is that right?
Self-training, yes.
Yeah, self-training, not self-supervision. Yeah. Like you're actually using a self-training process. Okay.
Similar to a self-training process, yes.
Yeah, okay, got it. Okay.
So Amanda was asking, was there any validation done on the synthetic data generated by Bonito for a downstream fine-tuning task, and how much noise was present?
That's a great question. So we haven't done any manual validation of the synthetic data generated. Ideally, we should be doing it to understand how much noise is present in the generated data set. But the way we've done it is slightly more different. Once we have the synthetic data generated, we then train the model on it and then measure the performance. So if the model performance improves, we sort of know that, okay, the synthetic data generated is actually better. So this is a more traditional way of measuring if the quality is good or not.
Thanks. I had another question on, was there any study you did on generalization of tasks themselves? Because I see most of it was around QA, right? Question answering. And did you see any in Bonito itself in being able to create or generalize to the tasks basically that it was, being trained on in prompt source or from prompt source?
No, actually, we didn't really try experiments beyond the 16 task types that were there. And among those 16 task types, we selected question answering or natural language inference because you can't really create synthetic instruction tuning datasets with an instruction tune model for these task types. For example, we also have the summarization task type in the Bonito training mixture, but you don't really need Bonito for summarization. So it does help in the training, but we didn't really do experiments with those types of tasks. So yeah, in just to summarize the answer, no, we didn't really check if our model generalizes to new task types.
Thank you.
So my question is, how similar were the domains of the fine-tuning data sets and the evaluation data sets? So like your example you gave with the medical text, right? In the evaluation, it seems to do well because the language model can, understand the semantics of this like very domain-specific medical text. But I'm wondering, like, you know, if we were to bring in completely unseen, like how do we do an eval for seeing like an unseen domain, like, and whether Bonito could generate, you know, an instruction tuning data set for like a truly net new domain?
Great question. So I don't think there will be, it's very unlikely there will be a completely new domain. But the way we try to ensure that these data sets, like these domains were sort of new, was we looked at the training data sets used to create Bonito or P3 or the instruction tune model, and we ensured that all the data sets in those in our test data set as well as the training data sets did not overlap. So that's the experiment setup. Does that answer your question? And we did not really have biomedical articles or like contract related data sets in our training data sets. So our model was able to generate you know, somewhat reasonable questions or even hypotheses in these specialized domains.
Okay, yeah, that makes sense. Thank you.
Yeah, I think I might have missed this, but I was wondering how you actually evaluate the quality of the data generated by Bonito. I think, for example, I think you gave an example with some medical text. You could probably have a trivial question you could generate from that. You could also have like more of a complicated question. So just wondering like how you do evaluations and compare those at least.
Yeah. So again, this is a great question. We did not really evaluate this by hand. Like the best way to do this would be to have like a domain expert, like a doctor or a scientist from like the medical space, and get them to annotate, okay, is this a good quality question or not? And then also the answer. So that's the best possible way. We do the evaluation of quality indirectly, which is we generate the synthetic data sets with the Bonito model, and then we train another model on these synthetic generated data sets, and then evaluate this on the actual test data set of like these data sets that are head out. And now if the performance improves, we say that, okay, look, the performance is improving, most likely the quality also is improved. If the performance drops, we say the quality is not as good. So that is sort of the indirect way we've evaluated the quality of the synthetic data sets.
Got it. Okay, that makes sense. Do you think this is, I guess, more of a gut check kind of question? Do you think there's a lot of room for improvement around there? Which is like, if you have subject matter experts that can like kind of rank these responses and give you the best ones, for example, and you fine tune on, you know, that subset of the data, would that perform better versus, you know, everything?
Sorry, I didn't quite understand that question.
So yeah, let me maybe rephrase it. So if you generate a bunch of questions, and let's say there's like half of it are really good questions and half of them are not so good, you still use that as input data for training or for fine tuning. If you could figure out the best ones and only use those, would that like improve results?
No, you're absolutely right. So we just, in our at least experiments so far, we just used all the data that was generated by the Bonito model.
Right.
But a better way to identify which are the good quality data sets or good examples and the bad examples, and just use the good examples. Now, there is no easy way to figure out what examples are good.
Right.
Because the generations are, you know, in text, unlike in the you know, traditional self-training space. You can have like a confidence over like, okay, this label has like higher probability compared to this label, so you just pick the ones that have the highest confidence and train the model on that. But here, since it's in natural language, we haven't really figured out how to select the best you know, sequences to train on. So there's no principled approach, and that's exactly an area that should be worked on.
Cool. Yeah. No, that makes sense. Yeah, I was interested to see if there's any like ideas on what you thought the lift would be if you did that, or if you think there's a lot of room for improvement there.
I can definitely see a lot of improvement, or a lot of room for improvement there.
Cool. Awesome. Really appreciate the presentation. Thanks.
Thanks.
Amanda, go ahead.
Thank you. Nihal, this is a great presentation. Thank you. I was wondering if there was any comparison with, GPT-4, for instance, is used pretty widely for, can be used for like generating tasks, right?
Yeah.
I saw this a section in your paper around generating tasks with GPT-4. Can you talk maybe a little bit about that?
Yeah, so that's a good question. So the way we had created synthetic data sets with GPT-4 is by prompting it in order to generate the synthetic tasks. What we found that it is very difficult to prompt it the way, like figure out the prompt to generate the exact type of tasks that we are looking for. So that was an issue. And when we trained our model on these synthetic generated data sets by just prompting, we couldn't really get really high performance compared to like our Bonito generated instructions. So maybe one way to improve that would be to like have more of an in-context learning with GPT-4 rather than just doing prompting. This again ties down to like what the main experiment of our paper was, which was zero short task adaptation. If it was maybe few short task adaptation, I would have done those additional experiments as well. So I don't have like results for few shot adaptation, but I suspect that will perform slightly better than the zero shot task adaptation.
Sure, thanks.
Pacific Room, go ahead.
Hi there. So thanks for the presentation. I just had, I'm going to summarize a little bit and tell me if I'm wrong and what I understood, and then have a quick question. So your kind of key innovation here is to be able to perform domain-specific adaptation at the instruction tuning phase, as opposed to doing some unsupervised training, pre-training with your domain-specific data. And this then avoids kind of your catastrophic forgetting. Because what you want to do is, as you mentioned, is you take a model off the shelf, which has been instruction tuned. That's a lot better to take. What I want to know, and maybe you had numbers, I just didn't quite see them. Did you compare at all taking a pre-trained model, maybe with or without the instruction tuning, performing that unsupervised domain-specific training, so exposed domain-specific data, followed by the ordinary then instruction tuning on top? So of course, we already have the data used for the ordinary instruction tuning, and seeing how that baseline compares to using Bonito and your method.
Yeah, great question. We did try this experiment and it didn't really work as well as training with Bonito.
Okay, do you know what like the difference in numbers were? Like, was it a big difference? Was it a...
It was as good as having the instruction tune model.
Okay.
I can check it, and yeah, I don't think there was. It didn't really make a difference. Like this was an interesting experiment we tried a couple of months ago, thinking that okay, what's gonna happen, but it didn't seem to make much of a difference. I was a little like, yeah, I was hoping there would be something more interesting, but we didn't really see that.
Okay, good to know. Thank you.
Huang, go ahead.
Hi. Yeah, great presentation. I really like the idea. Yeah, really appreciate it. Now I have a question on the test you're generating. So I see the examples on natural language inference or like Apple yes and no version. I'm curious, which makes sense because you're doing against like PubMed QA, like those kind of data sets. I'm curious, how can we generalize to text generation phase? You think, because in text generation phase, you only have the prompt and you have to generate the knowledge yourself. Whereas in this case, you have the knowledge inside the prompt in some way. So how do you think that would generalize, and how would that look like? I'm curious if you have any follow-up experiment or any thoughts. Thank you.
Oh yeah, thanks for this wonderful question. I don't really have any experiments on like more like text generation, or what I like to call it like more chatty responses. So I mostly focused on more traditional NLP tasks, like classification, like yes, no question answering, or information extraction tasks. So that's just been my focus with this paper. There are like a few more papers that are related to this area. There is a famous paper called Humpback. Well, it's not that famous, but a popular paper from Meta called Humpback, where they are doing text generation. They haven't released the model, but their idea is super similar to what we are doing.
Yeah, appreciate it. Yeah, because the reason I asked is
does
like,
that answer your
I would
question?
imagine, yeah, it is. And yeah, the reason I asked is I would imagine you use like some plan data, and those are very like short instruction or
yes,
like, yeah, which is curious. Yeah, thank you, appreciate it.
Yeah, no, thanks.
Chris, I think you had another question, right?
Yeah, I was actually just peeked at your Git repo after you posted it. And one thing I'm still curious about, you mentioned self-training loops. And so I'm curious what you meant by that, like what kind of self-training is happening, or is that like when the downstream model is the same as the base model, we can think of that as downstreaming, self-training, or is there something else kind of going on? Okay, got it. So I'm curious to that end, like, can we, if we have like smaller, have you tested this on much smaller models? And in kind of in the spirit of knowledge distillation, like, and how effective is this process when the model is actually dramatically smaller and less performant, maybe in some ways, like can actually learn how to do these tasks well from a kind of teacher type model like Mistral?
No, that's a great question. So what we observed was, even in our paper, we have comparisons with Mistral and Llama. Both are 7 billion model, but Llama actually performs worse than Mistral, even though they're the same size, right? And I did another experiment on my end, haven't put it on the paper, which is on the Pythia model for 2.8 billion parameters. The results actually are comparable to the size of the model. So there is are correlated with the size of the model. So there is a drop in performance compared to the Mistral models. So I don't have the exact numbers, but I did notice there was a drop in performance when we trained smaller models.
But a drop in performance compared to a student type model that was of the same quality as the base model, you mean, or a drop in performance on Pythia itself?
No.
Okay.
We increased Pythia by a significant margin.
Yeah.
But a drop in performance compared to like a Mistral 7B model.
Yeah, of course. Got it. Okay. Fair enough. Which would have been magical if you got it to be as performant. Certainly. Yeah. I think I kind of one follow-up question there is, if you were able to have some evaluation mechanism that looked at the accuracy of the synthesized answers and what also was being produced by the downstream model, what would you expect over kind of multiple self-training type iterations? Like, did you explore that at all? Is this kind of a single self-training path, or do you actually go through, could we imagine multiple loops in which the base model is updated to be the downstream model, and then you go through a couple different loops? Have you run any experiments like that?
No, that's a great idea. So training on multiple self-training iteration loops might actually improve the performance a little bit, and there will be like diminishing returns after point.
Yeah.
But I think what's stopping us right now is how do we identify what the good quality instructions are right now.
Yeah.
That once we figure out some heuristic or a mechanism to do that, we can then try the self-training in like iterations.
Yeah, like you need some mechanism that's independent, that's going to judge the quality that you can trust, it seems like, to really kind of measure that. Or unless you have some kind of community-driven effort where you're just spitting it all out and letting people label it. Would you want to use that to curate, or or just for measuring? Like, what are your thoughts there?
Curate what?
Or like, in other words, if you're going to feed data, if you can use the same model that you're training on to resynthesize instructions, would you might you want to like leverage some kind of mechanism for also making sure that everything getting through is kind of high quality? For example, if we think that, you know, there are some instructions that are really subpar, or even answers that are subpar, even though the instructions are good. You see what I'm asking? Or if you go through many loops, would you actually get into some kind of goofy mode where it's training itself too much?
Yeah, I haven't really thought a lot about it because I'm still thinking like the first problem is like, how do we even identify which one is good? Like, I think once we figure that part out, the next things we will just figure it out like automatically. Not automatically, but it will be an easier thing to figure out just by trying a few experiments.
Fair enough. Yep. Cool. Thanks.
Thanks
And
for
this is really cool
yeah.
work. Oh yeah, but and to echo what Amanda said, really cool work. So appreciate that. Appreciate what you've done.
Thank you.
Yep.
Okay, Nihal, I don't think we have any other questions. But yeah. So yeah, I'd like to conclude the talk. Thank you so much for taking the time to be with us today. Thank you for presenting. I think there was a lot of interest from our team because there was a lot of questions. But yeah, once again, thank you so much for being here. Thank you so much for taking the time and presenting.